In this video, we're going to be doing example 14.3 in the textbook, Good Weather, Good Tips. So let's start by reading the problem and then discussing what we're looking to do with this. Does the expectation of good weather lead to more generous behavior? Psychologists studied the size of the tip in a restaurant when a message indicating that the next day's weather would be good was written on the bill. Here are tips from 20 patrons measured in percent of the total bill. This is one of the three sets of measurements made, the others being tips received when the message on the bill said the next day's weather would not be good or there was no message on the bill. We want to estimate the mean tip for comparison with tips under the other conditions. So if you recall from an earlier unit, we did a similar problem. We had the same data for three sets of 20 patrons. One set got a good weather message on their bill, another set got a bad weather message, and one set got no message. And using descriptive statistics at the time, we calculated the mean and standard deviation and compared one set of 20 patrons to the other sets of 20 patrons. And that's all that we could do with the descriptive statistics. Now we're moving forward, and what we're being asked to here is we want to take it to the next step and be able to infer what would happen if we put this message on the bill for all patrons. So we want to use the data from these 20 patrons to estimate what would happen for all patrons. What would be the mean tip that all patrons would give? Now, as we've talked about, when we use a sample to estimate the population, we can't know whether it's 100% accurate. So what we're going to do is calculate a confidence interval within which the mean is expected to lie, as well as give a confidence level, the percent of confidence that the mean will actually lie within that range. So let's start to collect the information that we need to do our calculations here. So we're going to start here like we normally do. So we are looking for different values, and the mu is the thing that we don't know, so that's our question mark. Standard deviation of the population. Well, if we look further down in the problem, that we don't have that information in this screen capture right here, but further down in the problem they tell us that the standard deviation for the population is 2. We want to identify our sample size, and in this case our sample is 20. We then want to look for the population mean and the population standard deviation, because those are going to help us calculate the information for the sample mean and the sample standard deviation. Well, the sample mean, it does tell us further down in the problem what that sample mean ends up being, but keep in mind these problems aren't always just going to give you all of the information that you need. So what you may have had to do was to enter this data into Excel and calculate the mean from there. But we are given the mean later in this problem because it's an example, and that mean is 22.21. Now for our purposes, you could have entered this data into Excel and also calculated the standard deviation. But as we're doing this from more of theoretical perspective right now, we've been calculating the sample standard deviation based on the population standard deviation. So we've been saying that the standard deviation of the sample is the standard deviation of the population divided by the square root of the number of data values within that sample. So in this case it would be 2 divided by the square root of 20. And when we do that calculation, we're going to end up with 0.4472. And this is kind of the process by which we've been starting to do a lot of these problems. But now that we've moved a little bit further into this unit, what we've been doing is finding the sample mean, calculating the sample standard deviation, looking at our confidence level, which in this case they're asking us to identify a confidence level of 95%, looking at that confidence level and determining how many standard deviations away from the mean that is. And so in the past, what we would have done is we would have said that we have our estimate plus or minus our margin of error, and that would have yielded the confidence interval. And our estimate would be that the population mean is going to be the same as the sample mean, which is 22.21, plus or minus the margin of error. Now the margin of error is how many standard deviations away from the mean is that? How far away from the mean? Well, what we have been doing is saying 95 is 2 standard deviations away from the mean, and so we need to multiply our standard deviations by 2, which we will do here. And when we multiply the 0.4472 by 2, we get 0.8944. And this would be our confidence interval with a 95% confidence level. Now, as we've progressed into the unit, what we've been presented with is a new formula that basically kind of combines what we've been doing all into one formula. Rather than processing this as a series of steps as we have, where, you know, our first step was kind of to identify the, step one was kind of to identify all of the data that we had in our problem. That's supposed to be at 1. Step 2 was to calculate the standard deviation. Step 3 was to identify the confidence level and use that information plus the standard deviation to do step 4 and identify our confidence interval. Well, now we're going to find that there's a formula that, and this is what mathematical formulas actually are, is a way of doing, you know, combining multiple steps in one process. So the formula that they're giving us for a confidence interval now is x bar plus or minus the z statistic, z star, times the standard deviation over the square root of the number of values in the sample. Now, as we look at this, there's nothing new about this formula. This is really just building in all of the steps that we've had so far. So taking our mean, which comes directly down into, becomes our estimate. The z statistic comes from our 95%, and using that plus that times our standard deviation gives us this 0.8944. So really, like I said, this is now just combining all of these steps into one formula. And you can see that if we plug this in, we're going to get our estimate, our sample our sample mean is still 22.21 plus or minus. Now that we're using this z statistic, we know that rather than using 2 for the 95%, we're going to use the more precise value of 1.96 times the standard deviation of 2 over the square root of 20. And when we do this out now, we're going to get 22.21 plus or minus 0.88, and you'll see this is slightly lower now than what we had originally come up with, because originally we were using a 2 rather than a 1.96. So 22.21 plus or minus 0.88, which means that our tip percentage is going to be 21.33% to 23.09%. That's going to be the range within, the interval within which there's a 95% probability that our population mean falls. So if we were to somehow poll all of the patrons of this restaurant, this is where their tip would 95% fall when they received a message for good weather. So this new formula that we've been working with for this problem is really just a way of combining all of the multiple steps we've been doing into one formula and being able to solve from there. If you're not good with remembering formulas, then if you remember the process, you're still going to arrive at the same answer. Just remember that from now on we should be using the z statistic of 1.96 rather than 2 for a value like 95.